First Spin. Welcome to First Spin, a show where I learn how to use the parallax propeller without having any prior programming experience. Rather than do this on my own, I have enlisted the help of two experts. Will that work? You told me to change it.
I'm not going to complain this week. We'll just do what we're going to do.
Roy and Whisker. Woohoo!
We will happily answer your questions, Addie.
All right. Excellent. So we finished the block diagram last week. Talked a lot actually about hub and cog access and such. And now on to the next page. Shared resources. Huzzah.
Well, I don't know. I don't think I'm ready to go to the next page yet.
Why?
Because I'm not quite sure if it's been clear, like, that you've been coding in the background here from the stuff that you've been learning. So,
sure.
like, I know you've been writing programs. You've been putting up videos every week on some of your programming projects.
Yep.
If you guys want to see those, you can go over to tymkrs.com.
Yep.
There'll be links there. But so like you've been working on these little LED, RGB and blinking LEDs and all sorts of stuff. Did you have any questions more directly related to code you've actually been doing?
Well, I know that there's a table coming up with a whole bunch of the, I guess, commands, special purpose registers. So I think I was going to ask at that point.
Oh, okay.
Yep, because they've got the diras and all that
stuff you've been using all the time,
right? But just to let you guys know, I have been learning how to program really simple LED projects like Whisker was talking about. And pretty much just I was using the prop demo board, which I absolutely love. And just they have LEDs on board that you can blink on and off, on and off. I made it bounce like a ball. And then I made it act kind of like a heart. I showed the heart's, the cardiac conduction pathways, because I'm a cardiac nurse by day. And it's actually just a matter of turning things on and off. So super simple coding thus far.
Microcontroller programming tends to involve a lot of turning things on and off.
Right. Your very first program, if I recall, was actually only a couple lines of code that just turned on an LED and turned it back off again.
Yep.
Right?
Yep. And that was easy enough.
So she was pretty quick to pick up the format of the language, which is pretty simple. I mean, you've got typically on most programs, you're going to be setting your clock speed, your PLL up at the top, and then you're going to be declaring a couple of global variables, and
if you need
then you're going to be starting out a function with pub and just doing your pub main there, and probably some sort of repeat loop, and doing your stuff in there. And usually for the first program that you're doing, some waitcnt just for timing stuff, and being able to turn the direction of the pins to inputs or outputs, and actually setting pins to high or low. And that's pretty much where she's up to, is doing most of that kind of thing.
Yeah, and Spin makes it pretty easy to set the direction register and the input and output registers, because it literally has commands, dir A, and open bracket what pin you want, and close bracket, and then whether it should be input or output. Right?
And we have talked about these a little bit when we talked about the I/O pins, I believe, when Eddie was asking us about the pins. I think we talked about the DIRA versus the DIRB.
Yeah.
There is no port B.
Right. But I mean, the actual Spin commands are literally dir A equals some value to equal, to set it for the direction, and out A to write the value out. So it's pretty straightforward based on what we've talked about to go write your first couple of lines of Spin code, because they're literally what we've already talked about.
Right. So, I mean, should we go into it? Since you guys are
Well,
talking about it more than I had intended.
I think it's worthwhile to go through this next two pages because the second one, like you said, has a chart with all of those special purpose registers and the appropriate commands to work with them.
Okay.
So, you know,
so any noobs, it's not as intimidating as what Whisker and Roy have made it sound. It's actually, I can explain it because I'm the noob here. I got it.
We've just been more than willing to explain things at a deeper level just because we know it makes things a lot easier later on.
Yep.
Right.
And when somebody's first learning how to program, they expect it to be super difficult. So it's the perfect time to like teach them binary and hexadecimal and stuff like that. And they're like, oh, this is like hardcore. I understand you guys are really smart. And it's not that it's that hard. It's just that if you learn that stuff from the very beginning, everything else is so much easier.
Right.
Yep.
Stop scaring them, Whisker.
So the whole next page in the manual, page 22, we've pretty much covered everything on that page.
Okay.
It's just more words describing the same thing that me and Whisker have already explained to you.
Okay.
Just a quick note on the whole shared resources thing. You have common and mutually exclusive. It just means the common stuff is like the system counter clock. All the cogs can access it at any time.
Okay.
The mutually exclusive is hub memory. Each cog accesses it on its turn, and only it has access at that given time.
Okay.
That's what they mean by the mutually exclusive there.
That makes sense.
So,
because I was about to actually call fallacy to the common resources being accessed at any time because I was like, wait, hub memory cannot be accessed at any time by cogs, but that actually goes under mutually exclusive.
Right.
I get it.
And the common resources are the I/O pins and the system counter.
Okay.
So anyway, the next section there, we go over all the clock stuff, which we've talked about for actually setting up your, clocks and whatnot. And then the next section starts talking about the cogs and how much memory they have and everything that we've covered in the last several episodes. So when we get down to the next page, see this.
One second here.
Oh, okay. Go ahead.
1 second. So it's in system clock. It says the only components that you don't use the system clock directly are the hub and bus. They divide the system clock by 2. Why? It's the last sentence in system clock.
Right. The reason I was hemming and hawing there is because I wanted to read it real quick.
Oh.
Yeah, so the hub and the bus it's referring to there is the address and data bus. It just operates at half the clock rate for when it's doing its internal circuitry. So the circuit that is actually driving the hub and the actual transistors and everything in there, they run at half the clock rate. It's sort of a detail that's
just
important.
For fun?
It's just that's just the way it's not able to go at full speed.
Okay.
I don't really have a specific answer. We'd have to go ask
that's
the
fine.
chip designer, Mr. Chip Gracie, about
that's
the exact details.
I blame
of this.
Chip. It's that guy's
fault.
But
it's one of those details where it just it's not really pertinent to.
Yeah, I mean that's
doing,
fine. It just is what it is. And they mentioned it just in case anybody wanted to know.
Right. It's just like this document covers all of the details of the propeller architecture. Even if all you're going to do is spin coding, you wouldn't need to know all this. It's like we said earlier, it's just helpful to know it.
Right. Okay. So then cogs, let's see. Two kind of much, just pretty much. This pretty much puts words to the last diagram that we looked at.
Right, and we've gone over all this information pretty thoroughly until we get to the next page where we start talking about the actual cog memory layout, which is that nice little picture at the bottom there.
So what you're saying is, due to our excellent explanations, this is very easy now.
Right. Well, easier. Okay, so I'm good with page 22. Page 23. Each cog has its own RAM. The cog RAM holds a copy of the spin interpreter. Last 16 locations serve as interfaces to the system counter, I/O pins, and local cog peripherals.
Right.
What's the last 16 locations?
So you have the 2K of memory in a cog is better to think of it as 512 longs.
Okay.
Long being 4 bytes each.
Okay.
And the last 16 of those longs are the special purpose registers.
Oh, it's like in the table right below it.
Right.
Okay, I see.
And so your program goes in those first 496 addresses, registers.
You remember last week how we were saying it's kind of like street addresses, and each you know slot on there is a different house, and some of those houses are like memory where you can store things like your program or information.
Storage warehouses.
And some of them are special purpose. They actually do things.
Coffee houses.
Like controlled pin directions and that sort of thing. That's what you're looking at on the table there.
Okay.
Right.
The map.
So that the first we'll go down these special purpose registers in order. The very first one there, the par register, as it says, is the boot parameter, and this is sort of an agreed upon, not agreed upon. When you first start up a cog, this register holds the address that it will use to go access hub memory.
Okay.
And you don't really have to use this. It's just if you set it when you do a cognew, you set the value that this par register will get set to. Then the cog, when it starts up, will be able to read that register and use it to go get something out of hub memory or do whatever it wants with it. It's just a parameter that gets passed in when you first start up the cog.
That's probably more than a new programmer can wrap their head around, right?
My eyebrows are kind of shifting because I'm trying to figure out.
This is something
I'm sitting next to her in person here, and her head just like turned sideways, trying to go upside down.
Well, again, this book covers everything, including PASM, and you really only need to worry about that particular one when you're using PASM. For spin, we can just kind of ignore that.
So, Eddie, you remember how you were doing a cognew?
Sure.
In one of your programs there? If you were doing a cognew with PASM, you'd also be able to set this as sort of a past value for it to get started with. So when your PASM code starts up, your PASM code reads that particular register, and it gets that start up message that you passed along with it that was custom just for it. So when it starts up, it goes, oh, the first thing I need to do is check to see if there was any startup parameters passed over here with me and what they're telling me.
Wait, how can you set the parameter if the first thing you do is read the parameter?
No, the parameter that's being set here is the one that's passed into cognew when you're using PASM. It's an extra parameter on that instruction. And it sets this register, the special purpose register, and then when the PASM code starts up inside the cog, it then reads this register to then go access.
So okay,
its
so
parameters.
the main program, I'm gonna quasi equate this with spin. The main program has this parameter.
Well, the cognew command is a spin command, so
okay, that's
you don't need to equate anything. It is a spin command.
Okay. So main program, like pub main, has blah 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 par, and then you set the parameters, okay? And then when you spin off a new cog, the cog will know to read those parameters and use those parameters in its own programming.
See, I'm gonna show you in the manual here. It's past the point where we're at here, but if you look at the cognew command. And listeners, cognew is just like how you start off a program to run in its own cog. You give it either a PASM program or you give it a function to go off and do in spin. And it's got the, you say cognew, you say which method or function or whatever you want to call it, you want to send off, and a stack pointer, which we talked about last week. But also there's an optional parameter that you can list there, which is the parameter list, and that gets passed through this little special purpose spot in memory. You don't have to use it, but you can.
Right. And even after all this explanation, it's something that you generally just don't use in Spin at all. It's only for PASM programs.
Yep.
Okay.
And the only reason we explained it is that's the first one on this list.
Right.
After that, all the rest of these kind of make more sense.
I think it's useful to explain it because it helps for her to understand that there are, for almost every command that you're going to give, there's the options on that command that you almost always use, and then there's optional ones that you can use but you don't have to.
Mm-hmm.
Right.
And that's the important thing to take away from here. There's a lot more going on behind the scenes that you can have access to if you need to, but in Spin you tend not to make use of those low-level underlying tools.
Okay. Fine by me.
Right.
Addie's like,
Okay.
thank God I don't need to learn that.
All right. CNT.
So the very next one, that CNT, is the system counter
Okay.
that we talked about last week. And so when a cog reads that register, that address, it's going to get the value that's in the system counter.
What do you mean? Like what kind of value?
It's
like the clock?
Like we explained, it's
Like
a 32-bit number that increments once per clock tick, and it's just constantly incrementing and wraps her back around to 0 after it overflows the 32 bits. And that CNT register will have that value for that cog.
I think we talked about that like 2 weeks ago.
Maybe.
I guess it was 2 weeks ago, maybe. But so this is just the cog's way of accessing the system counter. It's in this special purpose register.
Okay. So this actually brings us to the program that I wrote. Because I guess
Right.
I've used this before.
Yeah, like
Yes, you
CNT
have.
Right.
is an alias for that spot in memory.
And it gives it means a number or it means an increment.
It means a number. It is the current value of the system counter.
Okay, but the system counter changes every single tick.
Right.
Yep.
But
So-
when you access it at that clock tick that you access it
Yeah.
with this CNT alias, it will be a certain value, and that's the value that you will get.
But then the very next line,
The value
have a
will
different-
incremented, but that's not important because you read it at one time and then you read it again later and you do a difference between the two and it tells you how many have gone by.
Huh. That's a little confusing.
Well,
Because
it's-
so for instance,
How else would it work, though? I mean, think about it. Like, electrically, how else would it work? I mean, it's got to do it that way.
it's continuously updating every clock tick, and you're just at the moment that you try to read it, you're going to get the value that it was at that time. And that's the important thing. You don't want to keep updating to the most recent value. You want the value that it got when you looked at it.
Okay, so for instance, to turn on an LED and have it wait there for, X amount of time, and I'll start talking about my code here.
Yeah, this is something you've done.
So to turn on an LED, you say out A, square brackets, the pin number, I used 16, equals 1 for being on or high.
Right.
Okay, and then I wanted it to be on for 2 million clock cycles, right? Plus
Right.
CNT.
So what
Well,
you're
that's
doing
what
there
I ended up writing plus
is-
CNT, but I didn't really understand why I
is
wrote it.
when that line executes, the first thing it's going to do there is actually get the value of CNT currently when it is running this command. Okay.
Oh,
and then it's
add
going
2
to
million
add
cycles.
2 million to it, and then it's going to sit there and do nothing until
Oh.
CNT is higher than that, right?
Oh. So the
Right.
command.
But it does take into consideration the looping and all that stuff, which we mentioned 2 weeks ago.
Okay.
Because CNT
So
loops
then,
over.
so then, the way I wrote my code was wait CNT, parentheses.
Wait,
two,
CNT is one word. It's a one word command.
Yeah, wait CNT. Parentheses 2 million cycles. That was just kind of arbitrary. Plus CNT. So I could do wait CNT parentheses CNT plus 2 million cycles.
Yes.
Yeah, both would work just fine.
But that
And
makes
the-
more sense to me because then it's like, okay, so you wait for the clocks, you wait for okay.
You gotta
Right.
remember like 8th grade math class when they explain the order of how to do things when there's parentheses involved. So like everything inside of the deepest level of parentheses happens at the same time, right?
Well,
Right.
I mean,
And then
yeah, I get that.
everything
Yeah,
at
I get
the
that.
the next level happens at the same
Yeah,
time. It
that's just
doesn't really
easy
matter
arithmetic.
the order
Right.
that you list them in the addition.
I
Right.
see.
Addition is, it doesn't matter what way you add them, they're going to end up with the same result.
Because
I
what
see.
it's doing in the addition there is it's taking, the value in one memory location, the value in another memory location, it's adding them together, right? It's literally adding those two
Right.
things together and putting them into, the what do you call it, Roy? The
The parameter for the wait count.
Well,
The input.
yeah, it's going to end up there. But, in an actual processor, it's loading those two things out of the memory into
An ALU.
into an ALU and, doing that thing.
Okay,
And then
so
dropping it back in to wherever you're assigning it to.
sure.
So, I mean,
All right,
it
so
really doesn't matter which order you list things in.
okay, so let me just summarize this. Okay?
Sure.
Summarize this Addie style. So count CNT references the system counter, and it doesn't matter at what point that system counter is. It just matters that it accesses it. So the system,
Right.
so the counter could be at 5, it could be at 10 million, it could be at whatever. It doesn't matter. So once it accesses it, so if I want the LED to stay on for 2 million cycles past that point, then I will
Right.
say CNT plus 2 million cycles. So whether that point is 5 or whether that point is 10 million, I will get an LED that stays on for 2 million cycles past that point with the wait
Right.
CNT command.
Right.
Okay,
And
easy.
and the way the other thing to clarify what we're talking about with the whole wrapping around, because CNT is a 32-bit value.
Uh-huh.
If you happen to read CNT and it equaled 4 billion, which is almost the end of the range of 32 bits,
Mm-hmm.
and then you added, 500 million to that,
Yeah.
it would wrap around past the end of 4 billion back to 0 and then go up 490,000 something.
Would
right?
that be a problem?
No, because
It's still the difference.
Well, yeah, the clock counter itself is going to count up till it gets to the end of 32-bit value and wrap back around to 0 and count up from 0 again. So the wait count is just waiting for the counter to equal the value you passed into it.
Gotcha.
And the value you passed into it is going to be, whatever the number in count was plus 2 million. And if that happens to wrap around, it'll just wrap around.
Got it. Cool.
So
I
there's
dig it.
you don't need to worry about it, being wrong or waiting for the wrong value or anything like that.
No,
Okay.
I'm sure there's probably some issues if you give it a number that's way too big, because then you're overflowing the ability to hold it in memory and blah, blah, blah.
Yeah, but it will just wrap it and it'll, at worst case, wait a little bit longer than you anticipated.
Okay.
Because at 80 megahertz, the count value wraps around once every 53 seconds or approximately 53 seconds. So sometimes when you write a program, if you have an error in your math, you might end up waiting, 50 seconds instead of 1 second, something like that.
Gotcha.
So that's one thing to look out for.
Okay. Well, that makes CNT make all the more sense, because I've been wondering why in the world I have to plus CNT instead of just say wait count 2 million cycles.
Right, because
and it makes sense.
Right,
I need a reference.
Right. You're waiting for the CNT register to equal some value, so you have to tell it whatever CNT is now plus some amount.
Aha.
All right, we got about 5 minutes left. We got time for another one of these.
In A and in B.
Well, we should probably skip to out A or dir A first, since you kind of alluded to it a minute ago before out A.
Yep.
So dir A is the register where you set 1 or 0 to equal it's an input or an output. We've kind of covered that in the past, but this is like showing you where it is in the cogs memory.
Okay.
And you've already done the command where you do dir A open bracket.
Square brackets, yeah.
Right, square brackets and then 16 in your case, and you set it as an output.
Right. Now, the way I set it as an output was with 2 tildes.
Right.
Tilde is just shorthand. 1 tilde being a a 0, and 2 tildes being a 1.
Yeah.
So by 0 you mean input, by 1 you mean output.
Right. So it's just
yeah.
It's a shorthand to allow you to just set the dir A to input or output without having to say space equals 0 and space equals 1, right?
Okay. So
it's very useful to, like, when you're setting a bunch of pins at the same time, when you're doing like DIRA bracket 0 ... 7 close bracket and then tilde.
Yep.
You'll be setting the first 8 pins to outputs.
So I have a question. What if you wanted to set pin 2, 4, and 6 to outputs? Would you have to do DIRA 2 tilde DIR 4 tilde, or is there like a better way more efficient way to do that?
Well, the simplest way is like you described, to have the 3 separate lines.
Yeah.
But you can also create what we call a mask, which is a 32-bit value that has the appropriate bits turned on to equal each pin. So each bit in the value equals a pin on the outputs. Starting at the bottom, you have pin 0 going all the way up to pin 31.
Okay.
So you can create a value that
sounds complex.
Well, it's just binary counting, right? I don't know if you're familiar with that. So if you want pins 2 and 4, then that value is 6, right? That has the 2, or I'm sorry, that's not the value of 6. You want the second and the 4th bits turned on, which is really the 3rd and the 5th, because you're starting at 0.
Basically, there's a lot of different ways to do this.
Getting a lot more complicated.
You can do it in binary, like by going DIRA : equals percentage, and then a 0 and a 1 for all 32 of the bits. You can set all 32 of them to specific values all at the same time with one little line of binary. Okay.
Right.
And you can do it. You can set every single pin to an output just by going DRIA tilde, and you'll just set everything to an output automatically. There's a bunch of different ways to approach this, and it's the sort of thing where we could probably have an hour-long show just on the different ways that you could address different bits in these things.
Right.
And
so, in other words,
we'll be picking them up as we go through other things too.
Right. Just as a little bit of homework, you can skip up to page 104 and 105 in the manual, where it covers the dir command in detail, and it will explain how to do the bit-specific bit patterns. And it's actually pretty simple in Spin, because you can actually draw out 0 1 0 0 0 1 1 0 and as a binary number and assign it to dira, and then it'll just work.
But the
But
main
why
thing to
would you
take
do that
away
if-
from DRI,
DIRA.
is that it sets the direction of the input or output pins. So if you're going to set them to an output, they need to be a 1. You know, that pin needs to be a 1 in this register. And if you want it to be an input, it has to be a 0. And if it's not set right here, it's not going to work right. Always set them before you use them.
Last question.
Right.
Why do you have to set them instead of just using them? Why can't you just use them and then, because based on what the program is saying, it'll become that?
Well, by default, they're all set as inputs when you first power on the chip. So if you're going to use them as an input, you can just start reading them. It's by convention that you normally set it the way you want it. But they will all be inputs by default. So if you want to use it as an output, you actually have to set it as an output.
So they default as inputs. And sadly, Addie, that's all the time we have for this week.
Pooh.
So we'll pick up on this next time.
Yes.
Thanks for listening, everyone. You can find this show every Tuesday at firstspin.tv.
Yep. And if you want any examples of the code, we have it pretty much all over. Just look for Toymaker Television. We have it on YouTube. We have it in our forums. We have it on our blog posts. And if you want to ask any questions, just let me know.
Yep, that's it for us for this week. Bye.
Bye.
See ya.